In this video, we're going to talk about another application of max flow, similar to the one we did in the last video, where we were trying to split the railroads by removing different stations. So in this particular problem, we're going to consider the vertex cover problem. We've discussed this problem before, but this time we're going to just be focusing on bipartite graphs. So just to remind you, a vertex cover is a subset of the vertices so that every single edge has one of its endpoints in C. So in other words, each edge touches one of the nodes in our set C. So in particular for a bipartite graph, one really obvious vertex cover is just pick everything in the left side. Because by definition of a bipartite graph, each edge goes from one side to the other. So if we pick everything in one side, well, each edge must be touching it. There are no edges hidden away over here. So we could pick all of L, we could pick all of R. Either way, that's one possible option for a vertex cover. But in general, that will be a very large vertex cover, and we want to find a very small one. Our goal is to find a minimum vertex cover. So how could we do this? Well, we want to use max flow to our advantage here. And one application of max flow we already know is computing maximum matchings in bipartite graphs. And so since we have a bipartite graph, a natural idea would be to somehow use a matching to solve our problem. And that's exactly what we're going to do. So just in the last problem where we used Menger's theorem, or more specifically, we proved Menger's theorem as a consequence of our algorithm, we're going to prove another famous theorem called Konig's theorem. And it says for a bipartite graph G that the size of a minimum vertex cover is actually equal to the size of a maximum matching. So what does this mean? All we have to do to solve the problem is solve the max matching problem in a bipartite graph. So our reduction is really nothing. We just pass in the exact same input graph into our maximum matching black box and then output whatever it outputs. So in particular, we're using the algorithm from class, which used max flow as a subroutine, and so it runs in O of V times E time overall. So although we'll end up proving this theorem, this is really just the key claim to prove our algorithm is correct. So we're not using the theorem, we're proving it. This just is the key idea to prove algorithm is correct. And this is very similar to max flow min cut. So again, we're going to end up unrolling our reduction to max matching and using properties of flows and cuts to prove the algorithm's correct. So the actual reduction here, the actual algorithm we're going to use, is just the max matching algorithm. But in the proof, we're going to think about what the max matching algorithm's actually doing. So although the algorithm is black box, the proof will be white box. We're going to use the fact that this reduction to max flow had a specific form. Okay, so let's start with the proof. Just like before, one of the directions of the proof don't even require max flow or min cut. We can just reason about it intuitively. So let's say you gave me any matching in our graph. So here's our graph, L and R, and I gave you these specific nodes in the matching, or these edges are in the matching. So remember, the definition of a matching says it's a set of edges so that no two edges share an endpoint. And since they don't share an endpoint, if we want them to be covered, we have to pick at least one node that touches each of these edges. We couldn't use less because they don't share endpoints. So if we just took these two and kind of hoped this edge would be covered, it would never work because we know these edges are disjoint. So the key idea here is, given any matching, the vertex cover has to have size at least the size of your matching M to cover its edges. So that part's pretty easy. Now, the idea again is we want to show that's also sufficient. So if you gave me a max matching, I want to be able to choose one endpoint for each edge to make a cover C. Now, intuitively, the reason this would work is, let's say there was some edge. So suppose some edge U to V was not covered. Well, that means U and V are both not in C. So U is not in C and V is not in C. But if this was the case, if neither of those vertices were in C, then that means both of these endpoints aren't in M either. So that implies that neither U nor V touch edges in M, and so M prime, which is M union the edge U to V, is a bigger matching. But that contradicts the fact that M was a maximum matching. So that's kind of the idea, and we can see that even without using max flows. But the issue here is, well, choose one endpoint per edge. Well, how do we actually do that? Maybe there isn't a way to do that. But this is the idea. So the idea is, if we hypothetically chose the endpoints just right, then we would be covering all edges. Now, to formally prove this, we're going to appeal to the reduction. So we're going to peek inside the black box and remember that the way the max matching algorithm works is it creates this network where we add a new source, we add this sink T, and then we have directions. We just take all the original edges and direct them left to right. So before we had capacities 1, and capacities 1, but for the sake of proof, we're going to make these capacities infinity. So this won't actually change the algorithm. For all intents and purposes, you can only send 1 unit of flow on that edge anyway, but for the purposes of the proof, the infinity will be helpful. So just like in the previous example where the infinities implied that certain cuts weren't possible, again, we're going to appeal to the infinities to make sure certain cuts aren't possible here. All right, so this is the reduction from max matching to max flow. And we can compute some max flow F star, and we can compute the corresponding cut S and T. So the cut's going to look something like this, and then T is everything else. So this is S, this is T, and this is L and R. So why does S have to look like this? That's because otherwise it contains an infinite edge. But we'll talk more about that in a second. So I claim that a vertex cover, C, we can take everything in S that's also in R. So for example, this node. And we'll also include nodes in T that are on the left side. So that would be like these two nodes. And I claim this is a vertex cover. Now, before we prove it's a vertex cover, what's the size of this cover? Well, we have one vertex, basically per saturated edge. And so the size of the cover, this is going to be equal to the capacity. Well, it's not exactly the capacity of the cut. So we're taking part. Okay, so it is equal to the capacity of the cut, yeah. So it's not equal to the set sizes, but it is equal to the number of edges that cross the cut, which is the capacity. So the size of the cover, which is the number of nodes we took, are in correspondence with edges leaving S and going to T. For every single vertex in the cover, we know there was one edge either going into it from S or leaving it and going to T. That's how we pick the nodes. All right, and what's the size of this cut? Well, because it's a min cut by the max flow min theorem, max flow min cut theorem, this is the size of the flow. And we know from the reduction that the size of the flow, we proved this already, is equal to the size of a max matching. And this equals the size of a max matching. Okay, so again here, this then proves that exactly what we wanted, that given a maximum matching, we can find a vertex cover of size at most that. So in particular, this is a specific cover, so the min vertex cover size is at most that, and so min vertex cover size is at most the size of a maximum matching. And so we have the size of a maximum matching is both, or the size of a min vertex cover is both at least the size of a max matching, and it's also at most, and so they're equal. So that will prove the claim. But first, there's this one detail where I claim it's a vertex cover, but we didn't prove that. And also, just to remind you, this is because of the max flow min cut theorem. So just like in the last proof, one direction was easy and the other direction needed the max flow min cut theorem. So let's now prove that this is indeed a vertex cover. So clearly some of the vertices are covered, the ones we put in the set, or all the edges touching these are in the cover. So let's suppose some edge UV is not covered. So this means, by definition, that U is not in C and V is not in C. And so by definition of C, that means U was not in L intersect T, and V was not in S intersect R. So it was neither these, nor it was these. So the only other possible option, if it doesn't touch any of these edges, would be if it was somewhere in the middle. That's the only other option. So this implies that U must have been in S and V was in T. So to give you an example of what this would look like, we would need an edge like this, where Actually, there's already an example of that. So in this picture here, we would need one node in S and one node in T with an edge crossing it. And so notice this specific edge, U to V, crosses the cut. That's exactly what it would mean. So we have a node that's in S, that's also in L. So let me rephrase this slightly. So we have U is in S and in L, and V is in T intersect R. But intuitively, you can think of it as it's in the middle, right? Because we took things in S on the right, things in T on the left, so the only other things left are things in S on the left and T on the right, and it would look like that. But clearly, if it does this, then this edge crosses the cut. But this edge has infinite capacity. The capacity of U to V is infinite, and so the capacity of S to T, which includes this edge because it crosses the cut, is also infinite. So this contradicts ST being a min cut. You can always find a finite cut. For example, just take all of these edges. Basically, that corresponds to picking every node in L for your cover. So one better option would be just to do this. This has size cut capacity at most size of L, which is finite. So if this was truly a min cut, it would not have infinite capacity. You can always find a finite capacity cut. And so this contradicts it being a min cut, and so every edge must be covered. So this implies all edges covered. And so C is a valid cover. So here we're using the structure of the cut, what it actually looks like, to prove that our constructed cover is truly a vertex cover. So in particular, like I said, the infinite capacities are not necessary if you just want to compute the size of a min vertex cover. But if you actually want to find a specific cover, construct the solution, then the infinities are necessary because you need to use this formula to construct it. So if we wanted to be more correct, the purple, this is not a valid cut, or at least it's not a valid min cut. It would have to look something like this. So you have to get a much weirder shape to now make it correct. That one's even not right either. So it looks like this. That's now valid because we see there's one edge here that go from S to L. And then we also have one edge from R to T, and nothing else is going to be crossing that cut. Well, except for that edge. So we would still have to finagle the drawing a little more. But as you can see, it gets pretty complicated, which is why it's important that we can use the formula. All right, and that's it.